Welcome to today's invited talk. Anuj Dawar was in IIT Delhi. He did his undergraduate there, and then he moved to University of Pennsylvania, where he did his PhD with Scott Weinstein. And since then, he has been in, he was in Swansea, and now he's in the computer lab at Cambridge. It's a great pleasure to have him here. We would, one of the things which Anuj got into early was finite model theory to complexity, and his early work was on finite variable logics, and now he has moved to an area which is much closer to parameterized complexity. That is, he's been working on tree width, locally bounded tree width, these kind of issues. And we have today's talk on the complexity of satisfaction, the satisfaction problem over sparse graphs. I welcome Anuj.
Hello? Yeah. Okay. So, for those of you who missed it, I've just been thanking Venkatesh and Saket and everybody else. But Fedor in his talk started by, listing the various other invited speakers who have spoken at this IWPEC before. I have to say this is the first time I've attended this meeting, and I'm really enjoying it. Now, in terms of topic, the closest one to what I'm going to talk about is probably one Fedor mentioned by Stefan Kreutzer, with whom I've worked quite a bit on algorithmic meta-theorems, though the word meta-theorem doesn't appear anywhere in my talk. Another writer, I wanted to add, some of you I know were at FSGTCS last year, where I gave an invited talk, and there is some amount of overlap between what I said there and what I'm going to say today, but I promise you there will be some things new as well. So now, as I said, so what is it, 2 years ago, Stefan gave a talk on algorithmic meta-theorems at this meeting. And what I'm going to talk about has a lot of overlap with that, but I don't talk of meta-theorems. I prefer to think of it, or I'll describe it, as looking at the parameterized complexity of one particular problem. And that is the satisfaction relation for first-order logic on graphs. Okay? So there will be a brief mention at some point of monadic second-order logic I'll make, but mostly I'm going to talk about first-order logic. And so what is the problem? The problem is simply this. You're given a graph, and you're given a formula, right, in first-order logic. And by first-order logic, I mean this language, right? It's a language where you have one binary relation symbol representing the edge symbol on graphs. You have the usual Boolean combinations, and you have existential and universal quantification of variables, and you can write down properties of a graph in this logic, in this specification. And you're given a graph and a formula, and you want to check whether this is true. And I'm going to ask, what is the complexity of this when parameterized by the length of the formula? Okay? So in general, we think of the graph as being big and the formula being relatively small. And generally, just to fix a bit of notation, I'll write n for the size of the graph. I mean, so usually this means the number of edges in the graph. I sometimes loosely use it to mean the number of vertices in the graph. It really doesn't matter, because first of all, I'm not really interested in polynomial factors. Moreover, mostly I'll be talking about sparse graphs where the number of edges is linear in the number of vertices. So just ignore the distinction. N is the size of the graph. I'll write L for the length of the formula, and M, which is bounded by L, means the depth of nesting of quantifiers inside the formula. So this is going to be an important measure of the complexity of a formula, is how deeply nested the quantifiers are. Okay? So now, this problem, what I call the satisfaction relation, sometimes called the model checking problem for first-order logic, is well studied, and it sort of, in some sense, encapsulates a lot of what we know about parameterized complexity. If you take the naive algorithm, the running time is about that, okay? It's the length of the formula times the size of the graph raised to the power of the depth of nesting of quantifiers, right? Ignore the L factor. I mean, that's really just to deal with the, I mean, you do this by recursion over the formula. The L is really to deal with all the Boolean cases and so on. The important n to the m comes from the fact that if you have m nested quantifiers, each one involves a loop over all the vertices of the graph, you know, testing the values of the variable. So you get n to the m. So it's clear, I mean, so you get the problem is in XP. In fact, it's AW star complete, it turns out. And it's kind of paradigmatic of hard problems in parameterized complexity because if you fix the number of alternations of quantifiers, now this is not the depth, but the number of alternations of existential versus universal quantifiers, you get sort of canonical problems which are hard for WT, right? So for all levels of the W hierarchy, you get by looking at the number of alternations of quantifiers. And it encompasses many of the standard graph problems which are studied in parameterized complexity. I've just written a few in the sense that whenever you have a problem where fixing the parameter, you can express the problem in first order logic, that gives you a reduction from the problem to the satisfaction problem for first order logic. So, I mean, vertex cover, if you fix the value of k, you can write down a first order formula which says there is a vertex cover of size k. And that's a reduction from vertex cover to satisfaction for first order logic. Independent set, clique, dominating set, network centers is just another name for what Fedor called R dominating set. So distance, you know, dominating with distance. These examples will reappear at some point in the talk. That's why I listed them. But of course, there are many others you can think of. Okay. So this means that, I mean, this is why, in some sense, people talk of meta-theorems, because looking at the complexity of this, of the satisfaction problem for first-order logic, or for some other general logic like monadic second-order logic, encompasses a wide variety of algorithmic problems that people are interested in. Okay. So the problem is hard. What I'm interested in, this is the second part of the title, sparse graphs, is identifying classes of graphs where it becomes fixed parameter tractable. Okay? And here on this slide and the next, I have a list of examples of the kinds of results I'm going to talk about, certainly not an exhaustive list. Right? So the idea is you restrict your graphs to come from some particular class C, and so now your problem is, you know, you're given a formula and a graph in this class and you want to decide this. And for many interesting classes, this turns out to be fixed parameter tractable. Okay, so you can get rid of the m in the exponent by considering restricting yourself to suitable classes of graphs. And I'll run through a few examples. I mean, the classical example is Courcell's theorem, and those of you who were at the school which preceded this, the conference will have seen an exposition of this. And this is for more than just first order, this is for monadic second order. I throw it in for completeness, but I'll really be only interested in first order. So this tells you that if you restrict yourself to graphs of tree width at most k, for any fixed value of k, then the satisfaction problem is fixed parameter tractable, in fact, fixed parameter linear time. The theorem of Zese says that you can get something similar if you bound the maximum degree in the graph by some constant k, right? So for any fixed constant, I write dk, right? So tk is class of graphs of tree width at most k. dk class of graphs of degree bounded by k. Again, first order logic is fixed parameter tractable. In fact, linear time, right? So the exponential dependence on the n to the m disappears, and it's. I should say though that the dependence on the formula length is very bad here. I mean, it's non-elementary, right? So it's a horrendous function of the length of the formula times the size of the graph is the complexity here. Okay. Now the thing is, taking these two as a starting point, the question is how far can we push this class C? How general can we make it and still preserve this nice property that first order logic is fixed parameter tractable? And here's a sort of series of results which I'm going to sort of quickly survey. Locally bounded tree width, which Kamal mentioned is introduction. There's a result of Freak and Grohe, which shows first order satisfaction is fixed parameter quadratic time. I should say this bound is improved by results down here. Okay, what local tree width bounded by a function t is, I'll sort of briefly tell you in a moment. Classes of graphs that exclude a minor, right? So or H minor free graphs, or I just say equivalently exclude some clique as a minor. That's equivalent. So write MK for the class of graphs that exclude the K clique as a minor. Then by result of Flume and Grohe, first order satisfaction is fixed parameter tractable. This n to the 5, I should explain perhaps a little bit. The n to the 5 comes from, it's really n squared times the complexity of testing the minor relation, which from Robertson-Seymour work comes to n cubed. But that's been improved. So you can actually replace this n by n to the 5 by something like n cubed log n. And again, this is actually improved by result down here. So but this was the complexity that they derive. And then this is a result we had with Martin Grohe and Stefan Kreutzer, which says if you look at locally excluded minors, again, I'll explain to you what that means in a little bit. You get first order satisfaction is in that running time, and this is just n times that one, right? Well, not necessarily the same function f, but so again, this is improved by what came later. And then a couple of recent results. One on graph class of bounded expansion. There's a paper in Fox 2010, and there's sort of independent work by myself and Stefan, which shows that first order satisfaction is linear time, is fixed parameter linear time on these classes. And as I said, this generalizes this, though it's probably incomparable with this as a restriction. And then I'm going to talk a little bit about nowhere dense graphs, which are sort of a generalization of all the above restrictions, where the question is still open of what the complexity of first order satisfaction is. But in a paper at FSTTCS last year, we showed that many of the natural problems you consider first order definable, including independence and domination problems and all the ones I had on the previous slide, turn out to be fixed parameter linear time. Okay. So we don't really have, we don't really have an example of a first order definable hard problem here. Gives us some hope that actually the problem is tractable, and but we don't know that yet. Okay, so this this sort of collection of results is what I'm going to briefly survey, and what I want to sort of emphasize is not so much the results, but the methods used to prove this, and the methods rely a lot on sort of understanding the structure of these classes of graphs. Now, cutting off around here in 2007, right? I used to tell this story. I mean, I gave an invited talk at CSL in 2007, in which I, up to this point, and I said there were really two methods for proving such results, and what I call the method of decompositions and the method of locality. These last two are proved using entirely different methods, right? So there's, as it were, new techniques have come into play, and so what I'm going to do in this talk is maybe in the first, spend the first 15 minutes, the next 15 minutes, I should say, sort of telling you a little bit about that automaton locality, and then the last half an hour explaining to you a little bit what these graph classes are, why they're interesting, and a little bit of the hints of the kinds of methods we use. Right, so that's my plan for the talk. Okay, so here is a little map to guide you along the way. So, take a snapshot of this into your memory. Well, I'll return to this map. You don't actually have to remember it. So here is a map of the restrictions on graphs that we consider. The arrows on this map are implications. And if an arrow is missing, that means that there is no implication. Okay, so the map is complete in that sense. It's not, there are no unknowns here. And to be precise, I mean, there's one slight looseness. If you consider these two restrictions, these are actual restrictions on graphs, right? You know what an acyclic graph is, or you know what a planar graph is, but that's a property of a graph. A graph is either planar or it's not. Everything else is not a property of a graph, but a property of a class of graphs, right? Having bounded tree width is a property of a collection of graphs that the tree, taking the tree width overall is bounded. Okay, but so read this as any collection of planar graphs has bounded genus, sort of by definition, right? Any collection of graphs of bounded tree width has bounded local tree width, right? This is, in fact, serves as a common generalization of bounded tree width, bounded genus, and bounded degree, as you see. Right? We have excluded minors over here, which generalizes bounded tree width and bounded genus, but is incomparable with either of those restrictions. These two are common generalizations of everything about expansion and locally excluded minors, and nowhere dense is a generalization of everything in this picture. Okay. So, as I said, I'll return to this map, when I need to refer to it. Now, something I've already told you, right? So the methods of proof for the list of results I had rely generally on two methods that are called method of decompositions, sometimes also method of automata, because in sort of the theorem, it's phrased in terms of tree automata. And then methods based on the locality of first-order logic. And then I'll talk about techniques for these bounded expansion and nowhere dense classes, which rely on things we call low-depth colorings or the wideness of these classes. Okay, so this is an of what we're going to do. Okay, so let's start again by restating Courcell's theorem, which as I said, many of you who attended the school over the weekend will have seen. So Courcell's theorem says that the satisfaction problem for monadic second-order logic, or even MS2, which means, so MSO is the extension of first-order logic with quantification over sets of vertices. MS2 is the extension of first-order logic with quantification sets of edges. Okay. In any case, satisfaction for them is fixed parameter linear time on any class of, on the class of graphs of tree width at most k. Now this, as I said, is often phrased, the proof is often given as an automata theoretic argument. You take a graph, the bound on tree width k gives you a tree decomposition, and then you have a tree automaton which say works bottom up on this tree and calculates, whether the formula, essentially the formula translates into an automaton. And therefore it works linear time on the size of the graph. Now, I'll give you another intuition. I mean, it's very much the same idea, but phrased without automata. And I'll say it for first order logic because I'm only interested in first order logic, but you could do this for MSO as well. Say you have graph G and a graph H and two tuples of vertices of length, let's say at most k, right? We write, this notation means that the two cannot be distinguished by any first order formula whose quantifier depth is at most m. So any formula that's true of this tuple of vertices in this graph, right? So I'm considering a formula with k free variables at the moment, right? So if the formula is satisfied over here, it's satisfied over there, and vice versa. And this is true for all formulas of quantifier rank m. The point is, by putting this bound on the quantifier rank, this is an equivalence relation of finite index. Because, in fact, once you bound the quantifier rank, there's only, up to logical equivalence, only finitely many formulas you can write. Okay, so this is a relation of bounded index. And then we can define for each k a finite collection of operations so that any graph of tree width at most k can be constructed from graphs of size at most k, or fewer than k vertices, through a sequence of these operations, right? These operations are sort of gluing operations. I have a kind of a picture. Well, I don't need to go there. Picture, right? You have a graph G1, graph G2, a gluing operation where you glue a small number of vertices at most k together, okay? You need a few other operations for technical reasons, actually naming certain vertices by constants at most k of them, renaming, erasing names, etc. The point is there's a finite collection of operations so that any graph of tree width at most k can be obtained from this finite set of graphs through these operations. And the important thing is that each of these, with respect to each of these operations, this equivalence relation is a congruence, which means precisely this, that if you look at two equivalent things, right, so G1 and H1, with a tuple of vertices x and y, capital X, capital Y, that are equivalent, and another pair, G2 and H2, and here this X is the same as that X. So G1 and G2, as it were, share some vertices. Then if you glue G1 and G2 along X, and glue H1 and H2 along Y, then these things are still M equivalent. Right? The point is that if a first order formula is true of this tuple in this joint graph, right, and these things are all named by constants, then it'll also be true over here. Okay? This requires some proof, and I'm not going to run through the argument. But this is the key to making a proof of this work. Okay? As I said, this is, if you will, an automata theory, automata-free proof. So what's the idea? To prove this, you have a tree decomposition, which gives you basically a way of constructing this graph from finite pieces. You start at the bottom, and you compute the M equivalence class, right, if you will, of the pieces, and go up the tree, gluing them together. Congruence fact tells you that the M equivalence class of each piece up the tree is determined by by just the M equivalence classes below. You don't need to know any more. And when you get to the top, you know the M equivalence class of the whole graph, and that determines whether the formula is true or not, because the formula has quantifier rank at most M. Okay? That's the essence of the proof, and this is, I call the method of decompositions. Okay? So stated in generality, it's the following. Suppose you have a class B, and you know that first order logic, I could state this in terms of MSO again, but I'm interested in first order logic. First order satisfaction is fixed parameter tractable on B, and C is a class of graphs which is basically obtained from B as a closure of B under some finite collection of operations. Okay? We need something more. We need that there's an algorithm which, given a graph in C, will compute a decomposition over B. Okay? In other words, because every graph in C can be described as, if you will, a term using these operations and the graphs in B, I'm also required that from the graph you can get this term. You can obtain the decomposition efficiently. And then for each M, this equivalence class is a congruence with respect to each of the operation. Needs something more. It has to be an effective congruence, which means that I can calculate the type or the equivalence class of this by just knowing the equivalence classes of the individual pieces. Okay? If these conditions are satisfied, then first order satisfaction is fixed parameter tractable on C. Okay, it seems like a sort of complicated set of conditions, but this is just to abstract a generalization from what's happening in the proof of Courcelles' theorem. In particular, if you take the class B to be the collection of graphs of size at most k, so that this condition is trivially satisfied, then you can get the collection of graphs of tree width at most k as the closure of B under certain gluing operations, and so on. Okay? Right. And I'll give you another instance of the method of decompositions, a more complicated one, in a moment. The other method, what I call the method of locality, is best illustrated by on bounded degree graphs. So, I've stated in this form. I should just say the first order satisfaction is fixed parameter linear time on graphs of degree at most k. This is now this is first order logic. This is not true for MSO, right? Unless p equals np. That's because graph 3 colorability is already np complete on graphs of degree at most 4, I guess, and 3 colorability is expressed by a single MSO sentence. So this can't possibly be true for MSO. Okay. Now the proof of this relies on the locality of first order logic, and so let me just tell you briefly what that means. This goes back to a theorem of Geifman from the early 80s that says that any first order formula can be expressed as a Boolean combination, or sentence just means first order formula without free variables, right? It's equivalent to a Boolean combination of basic local sentences. What's a basic local sentence? This is a basic local sentence, and this is to be read as there exists S elements which pairwise are far apart from each other, right? So the delta xi xj greater than 2r just means the first order formula which says that the distance from xi to xj is greater than 2r, okay, for some value of r. And then psi r xi means some formula psi where you have relativized all the quantifiers to the neighborhood. So this is basically saying this is a formula psi holds in the radius r neighborhood around the point xi. Okay? So it's some first order property, but only about the radius r neighborhood around a point. So this tells you that first order logic really talks only about local things. Right? The only thing you can say in first order logic is some Boolean combinations of statements which say there exists a collection of points, and around each of these points, something happens. Okay? Now, from this, one can extract, I mean, it's not straightforward, but I don't really have time to go into the proof. And this is the work of Freak and Grohe, really. You can extract what I call the general method of locality, and here's the principle. So the method of locality says, suppose we have some function which associates a parameter with each graph G, right? Some integer parameter. I just don't much care what. And say that we have, suppose the satisfaction problem is fixed parameter tractable when you take both the length of the formula and k as parameter. Okay, when might this happen? Just take a completely trivial k, let k be the size of the graph. Okay, if k is the size of the graph, this is trivially true, because if I'm allowing any function of the size of the graph, then I'm happy, right? Okay, but suppose this is true, then we define the class of graphs of bounded local k as those graphs for which there's a function, so that whenever you consider a vertex, sorry, this is v, so that should be a v as well rather than an a. Whenever you consider the R neighborhood of a vertex in a graph in this class, then the value of this parameter is bounded by T of R. Right? So in other words, we're not asking that K is bounded on the whole class, but in this class, whenever you look at a neighborhood of a fixed radius, you have a bound on the value of this parameter. Then using these two and Geismann's locality theorem, you get that the satisfaction problem on C is fixed parameter tractable. And the running time is just basically, you need an iteration of n over that in some sense. Okay? And that's why you get n to the c plus 1 over here. So what's an example? Say I take, as I said, k to be the size of the graph. What does it mean to have bounded local size? It means for every fixed radius r, there's a bound on the size of the r neighborhoods of a vertex. That's actually equivalent to saying that you have bounded degree, right? So a class of graphs has bounded local size if and only if you have bounded degree. As I said, if k is the size, this is trivial, right? In fact, you can take c to be 0 because you've got the size of the graph already in there. And so you get, on bounded degree graphs, the satisfaction problem is fixed parameter linear time, which is what I said Sayce's theorem gives you. But instead of size, suppose I take k to be the tree width of the graph. Okay? Now this condition is satisfied. This requires a little bit more work. I mean, in the sense that when I stated Courcell's theorem, all I said was that for every fixed k, you have a fixed parameter tractable algorithm. You need to look at it a bit more carefully to see that actually it's of this form, and that it's a single algorithm which is parameterized by both the length of the formula and the tree width of the graph. And it's linear in n. That gives you immediately that if you bound the local tree width, what does that mean? You look at a class of graphs where for every fixed r, the neighborhoods of radius r have bounded tree width, then you get a fixed parameter quadratic algorithm. Right? So this was Freak and Grohe's theorem, that you have so fix function t, we get the class of graphs of bounded local tree width by t, basically those graphs in which the neighborhood of any vertex of radius r has tree width at most tr. Now clearly anything of bounded tree width has bounded local tree width by just taking t to be a constant function. But there are other interesting things. Bounded degree graphs also have bounded local tree width, though they don't have bounded tree width, right? because actually they have bounded local size. So certainly taking that bound. Turns out planar graphs also have bounded local tree width, right? Because a planar graph of radius r has tree width at most 3r, it turns out. Okay? In fact, any bounded genus graphs also have bounded local tree width. So this is much more general than what we had before. In fact, if I quickly go back to our map, right? So basically what I've explained to you is that bounded local tree width generalizes bounded tree width, bounded genus, and bounded degree. And here we've got, by this argument, a fixed parameter, a quadratic algorithm. Okay. Okay. So that's what I call the method of locality, and as you see, we have sort of a number of applications of this method already. Now, excluded minor graphs, it's excluded minor classes, right, or H minor free graphs, as they're sometimes called. In order to parameterize this by a number rather than a graph H, I write MK to say, take the collection of graphs which don't contain a K-clique as a minor. Okay? And obviously for every H minor free class, there is a K, so that it's included in MK. Now, here we rely on a theorem of Grohe, which says that, I mean, this is based on the Robertson-Seymour decomposition of H minor free graphs, that any graph in here can be decomposed of graphs of almost bounded local tree width. I'm not going to tell you exactly what this means. It's a rather non-trivial definition. And then it turns out that you look at this decomposition, it basically decomposes the graph into pieces which have almost bounded local tree width. And it turns out you can define operations, I should really say operations here, non-trivial operations, for which, so that you can describe any graph as being composed of these pieces by applications of these operations, and then you get sort of this M equivalences, congruences, and this turns out to be then a direct application of the method of decompositions, that first order logic is fixed parameter tractable on MK. Okay? So basically it's the fact that you can decompose these graphs into pieces which have bounded local tree width, and bounded local tree width, as I just showed you, it's sort of fixed parameter tractable. And as I said, they got a running time of something like n to the 5, which really comes from combining the n squared for bounded local tree width with the n cubed for the testing whether one graph is a minor of another, which comes from the Robertson-Seymour work. Okay. Now, so this excluded minor, even though they're built up, as I said, by decompositions over things of bounded local tree width, actually it's an incomparable restriction with bounded local tree width. Already bounded degree is incomparable with excluded minors, right? Graphs of degree at most 3 don't exclude any minor. So there's a natural question was, is there a common generalization? And this is what we did in in this work. Basically define a sort of common a kind of obvious thing to do. Define the class of graphs that locally excludes minor. So basically you have a function t, and you say that the R neighborhoods around a vertex in a graph exclude TR clique as a minor. Again, so it's not that the class of graphs excludes some fixed minor, but for every fixed radius of neighborhood, there is a minor that's excluded from all neighborhoods of that radius. Okay? That's what we call locally excluded minors. And it would seem to be a direct application of the method of locality, right? Because if we have fixed parameter tractability for excluded minors, applying this should give it to us for locally excluded minors. Except there's a catch. And that's, again, in order to apply this, we need this algorithm to work as it were a single algorithm which works for all values of k. And that's not what we get from the Flume-Grohe theorem on excluded minors, which simply tells us that for each k, this thing is fixed parameter tractable. And we don't really have the single algorithm because it depends upon certain, if you will, black box properties of this Robertson-Seymour theorem, which we don't know necessarily how to compute. So this is just to tell you that in order to prove this, we required a non-trivial new decomposition theorem of excluded minor classes, but which then is sort of all computable and allows us to apply the locality method. Okay, so that was my sort of review of the, as I said, the two methods, decomposition and locality, which got us this far, okay? And if you think about this, what this is saying that you start from classes of graphs of bounded size, which is a trivial thing, apply the method of decompositions to lift it to class of bounded tree width. A method of locality gets us up to bounded local tree width. Another application of the method of decomposition took us to excluded minors, and then another application of the method of locality got us up to locally excluded minors. Okay. Now, I'm going to tell you a little bit about what these what these graph restrictions are, why they're interesting, and in particular, a sort of powerful new method emerges over here, which I'll call the method of low-depth colorings, which gives a much more powerful result because even though this restriction generalizes excluded minors, we managed to extract a fixed parameter linear algorithm for first-order satisfaction, which is much better than what we had over there. Okay. And here, as I said, we still don't know, but we're working on it. So to motivate the definitions of these two classes, because the definitions themselves look a little bit obscure, I'm going to talk about sparseness in graphs, right? Sparseness, in general, we say that a graph class is sparse if the number of edges grows at most linearly in the number of vertices, okay? So this is just notation, right? Single vertical bars means the number of vertices, double vertical bars means the number of edges in G. Now, obviously, if you bound the degree, then the number of edges is linearly bounded in the number of vertices. That's kind of a trivial fact. If you bound the tree width, you also bound the number of, the number of vertices bounded by the number of edges is bounded by k times the number of vertices. This is, again, not too hard to see. And that's because any graph of tree width at most k must contain a vertex whose degree is at most k, right? And then, so you remove that vertex and all the edges incident in it. You haven't increased the tree width, so you still have a vertex whose degree is at most k. Repeat this. At each stage, you remove a vertex. You remove no more than k edges. At the end, all edges and all vertices are gone. That proves this. More generally, it's true that if you exclude a minor, then the number of edges is at most linear in the number of vertices. This is rather less straightforward to prove, but this is sort of a standard known result. It's 2 paragraphs in Diestel's graph theory book. There's much more on it, on obtaining exact bounds on the function f. But the point is there is a function f, so that for every r, if the average degree of the graph is greater than fr, then it contains kr as a minor. So if you look at the graphs which exclude kr as a minor, you have a bound on the average degree, and that, of course, means that the number of edges is linearly bounded in the number of vertices. Okay. F is of the order of square root of r times log r, is I think the best bound. Okay. So now, say that a class of graphs is sparse. So the point of this was just to tell you that most of the classes we've been considering are sparse in this sense. I say most because this doesn't apply to, say, bounded local tree width. Okay. Bounded local tree width are not necessarily sparse in this sense. They're sparse in another sense I'll get to in a moment. Okay, so say that a class of graphs is sparse if there's a linear bound. I've already said this, which is equivalent to saying that it has bounded average degree. Now, one one might say intuitively, well, what about just taking the sparseness as our restriction rather than these esoteric restrictions I'm now going to define? And first of all, I want to tell you that that's not interesting, right? Simply because they're pathological sparse classes. Take the class of graphs which contains for every finite graph the union of G with a number of isolated vertices equal to the number of edges that appear in G. Right? This is now a collection of sparse graphs, but it contains, basically it contains every graph along with a whole bunch of isolated vertices. You're never going to get any interesting structure out of this. Okay? So sparseness by itself is not an interesting restriction. Here's something maybe a bit more interesting. To get rid of that pathological case, we say that a class of graphs is hereditarily sparse if there is some constant so that for any graph in the class and any subgraph of that graph, we have the number of edges is C times the number of vertices. Right? That gets rid of that pathological example I just mentioned. Right? Turns out this is still much too rich a restriction because of the following example. So associate with any graph its incidence graph, which is simply the graph whose vertices consist of the vertices and edges, and the edge relation is the incidence relation on that. Another way of saying the same thing is Ig is obtained from G by taking every edge and inserting a vertex in the middle of it, subdividing every edge into two. Okay? Now it's easy to see that the collection of incidence graphs is sparse and in fact hereditarily sparse. Right? It's sparse for the obvious reason that you've just added a vertex for you've doubled the number of edges, but you've added a vertex for every edge there was, so the number of edges is now at most twice the number of vertices. And taking subgraphs, you'll always, this bound will be maintained. But the trouble is that the incidence graphs contain all the richness of the original graphs in the following sense, that if I want to evaluate a first-order formula on all graphs, I can easily translate it into a first-order formula on the incidence graphs. There's an easy, trivial reduction from the satisfaction problem on all graphs to the satisfaction problem on incidence graphs. So the problem on incidence graphs is as hard as all graphs. So I'm not going to get any traction by just requiring things to be hereditarily sparse. Okay, so we need something more. And it was sort of considerations like this that led to the definition of bounded expansion, which I'm going to get to in a moment, which comes from work of Nechetril and Osona de Mendes. Though they were not looking at the problem of first-order satisfaction. They were not interested in logic. They were interested in graph coloring properties. It was sort of combinatorial questions that inspired the definition. But to motivate the definition, I need to give you some other little definitions. So remember what it means for graph H to be a minor of G. Graph H is a minor of G if we can find inside G a collection of disjoint and connected subgraphs, call them BU, one for every vertex in H, so that whenever you have an edge in H, then there is an edge between some vertex in BU1 and BU2, right? Whenever U1, U2 is in it. This is sort of a definition, if you will, of a graph minor. And these witnesses we call the branch sets that witness that H is a minor of G. Now I'm going to say, suppose that you can choose these branch sets in such a way that each of them lies within the radius R neighborhood of one of its elements. In other words, these branch sets themselves have small radius, bounded by R. Then we say that H is a minor of G at depth R. Right? Sometimes say it's a shallow minor. Okay, H is a minor of G, and the witnesses have small radius. That's what it means to be a shallow minor. Okay, so the class of graphs of bounded expansion is defined as this. You require it to be hereditarily sparse, but you also require that for any fixed R, if you look at the collection of depth R minors of graphs in this class, then that collection is also sparse. Right? So the number of edges is bounded by some constant times the number of vertices. That constant depends upon the choice of R. Okay, but for each fixed R, you look at the depth R minors you get, and they are sparse. So first of all, I want to explain to you, this might help motivate the definition, why that rules out this example. The class of incidence graphs is sparse, it's hereditarily sparse, but from the incidence graph, you can recover the original graph as a depth 1 minor just by contracting neighborhoods of radius 1. So the collection of depth 1 minors of the collection of incidence graphs is already the collection of all graphs, and so it's not sparse. Okay? So the definition of bounded expansion basically says that contracting neighborhoods of radius of any fixed radius, you still get a sparse class. Okay. So now, to see that this generalizes, I mean, this specifically generalizes to, and this was the motivation of Neschetler, Lenzau, and Mendes, generalizes excluded minor classes because they're sparse, and obviously they're closed undertaking minors, so all depth R minors are also sparse because they're already included in the class, right? So you can actually take this delta R independent of R. It depends only on the minor you're excluding. If you bound the degree, you don't exclude any minors, but it turns out that contracting neighborhoods of fixed radius, you still always get a sparse class because think of it this way. If you get a graph as a minor by contracting neighborhoods of radius R, when you contract a neighborhood of radius R, the number of edges leaving this neighborhood is bounded by something like k to the R. And therefore, the largest clique you can get as a minor by contracting neighborhoods of radius R is going to be less than this. And then, well, actually, sorry, never mind the clique you can get. If you contract neighborhoods of radius R, you still have bounded degree. Maximal degree is at most k to the R. And so, obviously, bounded is therefore bounded average degree. So bounded expansion generalizes these two, otherwise, these two classes are incomparable, and it's a common generalization. Now, as I said, the recent result by these three people shows that first order satisfaction on this is fixed parameter linear time, and as I said, this improves the bound on excluded minor classes because this is less restrictive than saying excluded minor. And as I said, the technique is quite different. Now I see I need to make a decision on what I'm going to cover in the remaining 10 minutes because I'm not going to do everything I intended. Well, let me tell you a little bit very quickly about this. As I said, this is in bounded expansion classes. Let me skip this. Let's have a look at this theorem of Neschetler, Lenzau, and Mendes. If you have a class of graphs of bounded expansion, then there's a way of coloring the graph. Fix any p, right? This is an integer p. Then there is some number n, so that you can color a graph using n colors. Okay? So n depends not on the size of the graph, only on p. And this coloring has the property, it's a proper coloring, but much stronger than that. So, right? So each individual color is an independent set. But each collection of at most p colors has tree depth less than p. Never mind what tree depth is. All you need to know at this point is that tree depth in particular implies that the tree width is also bounded. In fact, the path width is less than p. Okay? So the thing is, it turns out that there's a way of coloring it so that one color gives you an independent set, two colors give you something of tree-like, three colors gives you something of tree width at most 2, four colors give you something of tree width at most 3, and so on. Up to some bound p, right? And you can choose p to be anything you like. It's just that the number of colors n you need grows with p. But crucially, it doesn't grow with the size of the graph. Okay? And this is the property, this property of low tree depth coloring, which turns out to be very powerful and gives us a way of evaluating first order formulas. So I'll give you a very quick example. If you just have an existential formula, right, so you have a sequence of existential quantifiers and then something that's quantifier free, it's easy how you evaluate it in a graph. You take Q, the number of quantifiers, and now you choose a coloring which guarantees that any Q colors have small tree width. And then for each collection of such Q colors, you take the subgraph induced. Because it has small tree width, you can evaluate this first order formula, right? And the total number of such total number of such subgraphs you need to consider is n, the number of colors raised to the power q. All of this is just parameter dependent, doesn't depend on the size of the graph. And at the end, if this existential formula is satisfied in the graph, it's satisfied by one of these subgraphs, because if there exists q elements, there exists, some set of q colors that they have. So this works for existential formulas. Doing it for, once you introduce quantifier alternations, requires significantly more work. And essentially, the question is, what do you do with a universal formula? Well, it turns out that you use the property of tree depth to show that you can convert a universal formula to an existential one. This allows you to get an equivalent existential formula, which is much larger in size, but depending still only on the number of colors, and so it's still only dependent on the formula. Okay, that's, as I said, a very quick overview of how this is done. But essentially, the power of the method comes from that low tree depth coloring theorem of Neschetiller, Nothomb, and Mendes, and we've done away with requiring this Robertson-Seymour decompositions. This includes, as a special case, the excluded minor classes. Okay. So now, nowhere dense classes are the ones that as I said, they were right at the bottom of my picture. In particular, okay, bounded expansion classes are still sparse in the sense that I defined. And I told you that bounded local tree widths are not sparse. So they turn out to be incomparable. So we have these two maximal results in my picture. First order satisfaction is fixed parameter tractable on bounded expansion classes and on locally excluded minor classes. This is a definition that does generalize both of them, but we don't have the result for first order satisfaction on this yet. What's the definition? Again, take a class of graphs and take the depth R minors of graphs which occur in C, right? In the definition of bounded expansion, we required that this class is sparse. Now we make a much weaker requirement, just that this class of graphs is not the class of all graphs, okay? For any fixed R. So remember again that with incidence graphs, just contracting neighborhoods of radius 1, we got the class of all graphs. So we want to, this is a way of ruling that out, but saying it gets ruled out at any radius R. That's the definition of nowhere dense. Okay? So in other words, for each R, there is some clique that cannot be obtained as a depth R minor of a graph in C. Okay, this turns out, this clearly generalizes bounded expansion, because bounded expansion was the additional restriction that this class is sparse. It also generalizes locally excluded minor, because you can show that if something appears as a depth R minor, then actually it appears as a minor inside the neighborhood of radius at most 3R plus 1, right? That's not too hard to show. So if you locally exclude minors, then your class is nowhere dense. Okay, why is this an interesting class? Well, this is the theorem, again, this is due to Neschetiller, Nothomb, and Mendes, which shows that there is something very natural about this as a notion of sparseness. Note, it isn't sparse in the sense I mentioned before, that it does admit classes of graphs where number of edges grows more than linearly. But they define the following measure on a class of graphs C. I mean, it seems a bit of a complicated definition, but I think the theorem justifies the complexity. Take the log of the number of edges over the log of the number of vertices, right? So this is a number somewhere between 0 and 2 for any graph. Now take all CR is the collection of all depth R minors of C. Among all graphs in CR, take the lim sup of this, right? So see how high this gets. And take the limit of that as R goes to infinity. And what Neschetiller, Nothomb, and Mendes prove is that if you start with a collection that is infinite, any infinite collection of graphs, this limit is always defined. For any infinite class of graphs whatsoever, this limit exists and takes one of the values 0, 1, and 2, nothing else. Right? They call this the trichotomy theorem. Every infinite class of graphs falls into one of three classes on the value of these limits. It's either 0, 1, and 2. And the nowhere dense classes are exactly those for which it doesn't take the value 2. Okay? So as I said, this kind of justifies that there is a notion of sparseness for which nowhere dense is the natural limit. Okay. Well, so what we would really love to prove is that first order satisfaction is FPT on nowhere dense graphs. We haven't got this. What we have got is for most of the natural examples we can express in first order logic, a proof that it is indeed FPT. And this was, as I said, in a paper we had in FST-TCS last year. And there were various other domination problems, connected dominating set, Roman domination, etc. A variety of domination problems we considered all turn out to be FPT. And the proof was based on yet another technique, not decompositions, not low tree depth coloring, but a notion of wideness. Let me quickly run you through this through definition to illustrate. How much time do I have? 5 minutes. Okay, that should be enough. So suppose you have a graph. We say a set of vertices are scattered if basically their R neighborhoods are disjoint. So they're at least distance 2R from each other. Okay? And we say that a collection of graphs is wide if for any R and M, any graph sufficiently big in the class contains M vertices that are R scattered, right? So if you have a large enough graph, then you can find a large set which is far apart from each other. And the obvious example of this is graphs of bounded degree. Okay? If you bound the degree of a graph, then within distance R of M elements, there's only a certain size you can get, and in anything bigger than that, you'll find M elements which are far apart from each other. I mean, you can do the exact calculation, but it's clear that graphs of bounded degree are wide in this sense. Trees are not wide for the obvious reason that you can have a single vertex which is neighbor to, a single vertex with a lot of leaves, right? And so everything is distance 2 from each other, and you can be arbitrarily big, right? The size can be arbitrarily large. But trees have the property that actually, if I don't have a large scattered set, I only need to remove one element to create a large scattered set. Okay? Ever. In the sense that if I have a node of large degree, I remove that node and I create a large scattered set. If I don't have a node of large degree, then a big enough tree, I'll have a very long path, and on that path, you'll find a large scattered set. Okay? So I only ever need to remove one element. This justifies the notion of almost wideness, which says that a graph class is almost wide if there's some set S. And now, again, for every R and M, and any graph in the class which is big enough, I can find S vertices whose removal creates an R scattered set of size M. Okay? So trees are almost wide with S equal to 1. What about planar graphs? Any idea? Planar graphs turn out to be almost wide with S equal to 2. Right? This might seem surprising at first. In any large enough planar graph, there are at most two vertices you need to delete to create a large scattered set of any size you like. Okay? The proof is quite general and actually shows that depending upon what cliques you exclude, if you exclude a K clique as a minor, then you need to exclude, you're almost wide with S being at most K minus 2, which gives you for planar graphs the value of S equals 3, but you can improve it, because if you exclude K, if you will, the complete bipartite graphs on two sets of K vertices as a minor, then you're almost wide with S equals K minus 1, and that gives you the result for planar graphs. Okay. So I define wide and almost wide. So excluded minor graphs classes are almost wide. A further slight relaxation is if we let the value of S, the number of vertices you delete, depend on the radius of the scattered sets you're looking for. Okay? And that's a definition that I call quasi-wide. And you can then prove essentially the same proof that shows that excluded minor classes are almost wide shows you that any class of nowhere dense graphs is quasi-wide, right? So depending upon the radius you're looking for, there's a small number of elements you need to delete to create a large scattered set. And this is essentially what allows us to prove, to extract this sort of fixed parameter algorithm for the domination problems, which I'm not going to have time to run into. But then there's this result of, again, of Neschiter and Osorno de Mendes that shows that quasi-wideness is almost the same thing as nowhere denseness. As long as you're looking at graphs closed undertaking induced subgraphs, these two notions are equivalent. Okay? And that's my concluding slide. So this is the picture as we have it so far. As I said, we've been trying to push the boundary of what classes of graphs admit a FPT algorithm for first order satisfaction. That's the class of graphs I've considered. There are other examples which don't fit into this picture, right? I could have mentioned bounded clique width, for instance, but bounded clique width is not a sparseness condition. Okay, it's something of a different character. And there is reason to believe that this is a natural limit to notions of sparseness, but here the question is still open, and we're still working on it. Okay, that's. Right. I haven't talked of p-tasses, right? Sort of, you're looking again at first order definable problems and looking for p-tasses. I mean, I don't know. I mean, well, we have the result for excluded minor classes, right? I don't know if anything that even works for bounded local tree width or even bounded degree for that matter. Yeah?
So when you say excluded, when you say like up until excluded minors, right?
Sorry?
So when you say up until excluded
yeah.
minor, then you say this, like, when you're not, for example, then you, because that contains bounded degree.
No, it doesn't. There's no arrow from bounded degree to excluded minor, right? As I said, already graphs of degree 3 don't exclude any minor.
So that's where it always stops.
Yeah, well, this is right. So we have the result for excluded minor, and yeah, that's right. Any infinite class of graphs.
So can't one just take class of graph where this number is say 1.5?
Well, the theorem tells you that there isn't such a. I mean, that's exactly what the theorem tells you. It's impossible. Okay.
This number, will vary between say.
Yeah. Well, I mean, there is a bit of a trick here in that CR is a collection of graphs which are basically depth R minors of C. So you've already built in this notion of shallow minors into this definition. But the point is, if you look at this, what do I want to say? If you look at the collection of depth R minors of graphs in the class, then the collection of, the depth R minor relation is not transitive, but it has the property that if G is a depth R minor of G1 and G1 is a depth R minor of G2, then G is a depth at most 2 R minor of G2, okay? And since you're taking the limit as R goes to infinity, if it turns out you're excluding, which is the definition of nowhere dense, CR is not the class of all graphs, then essentially, well, I mean, this is a very hand wavy. You get in the limit, the thing can't exceed 1. But on the other hand, if at any stage CR is the class of all graphs, then this hits the value of 2, and it's going to be 2 for all greater values of R. So this already proves that you can't get a value between 1 and 2. For any class. It requires rather more work to show you can't get anything between 0 and 1. But this is a bit hand-wavy, but that's really the beauty of the theorem is it requires no assumptions on C other than it's infinite.
And you obviously tried to extend your result to first order formula.
Yeah.
So can you somehow express the reason why
Well, okay. So there's we essentially tried two different things so far. One is to extend this, and I have to sort of make a bit of a confession here. So this theorem on bounded expansion, which, as I said, appears in this Fox paper by Shaw and Thomas. We sort of got this independently, but we thought we were able to do it for the whole nowhere dense class, and we kind of announced that. And then because we discovered the bug in the proof, we didn't submit it, and they had the theorem, so they get the paper. Now, the trouble with this, with extending this low tree depth coloring method to nowhere dense classes, is in this quantifier alternation. Here, crucially, you replace a universal formula with an existential n, you get a blow up in size, and because with bounded depth, you have this n as a with bounded expansion, this n is a constant. With nowhere dense, the best we could do is n to the delta for arbitrarily small delta, where n is the size of the graph, and that's just not good enough, right? Because this thing, the size of the formula then becomes dependent on the size of the graph, and you're lost. Okay, that was what failed. The other thing we tried was to use this notion of quasi-wideness in combination with locality to get the theorem. And this is how we came across, this dominating set and so on. What this quasi-wideness allows us to do is, depending on the first order formula, you extract a value of R, which is really the Geisman locality of the formula. That gives you a fixed value S of elements to delete, which create a large scattered set. So S depends only on the parameter. And then, because this is a large scattered set, effectively what happens around each neighborhood is independent. And in terms of domination sets, this turns out to be a nice, this gives you easy kernelization, because, these things are far apart from each other. So if one of them, if they're dominated by a small number, this domination must be through this small set you've eliminated. And you can look at the distances to that, and if two things have the same distances, you can throw away one without losing any information. All right, so that gives you a sort of kernelization. But for first order properties in general, rather than domination, just distances to these S turn out to be not enough. You in some sense have to look at all first order properties of this neighborhood. But we don't know anything, we don't have any handle on what happens in this neighborhood other than it's still nowhere dense. And the recursion fails at that point. So this is a bit hand wavy. If we had something which gave us that the radius R neighborhoods we get through this in this scattered set have some nice structural property which allows us to evaluate first order formulas in those neighborhoods, we'd be done. But it turns out all we know about them is that they're still in this nowhere dense class, and that's not enough. Okay, it's
Of the morning with Stefan Zeider from Vienna, and he will present a work that he did with some English group on parameterized complexity for general factor in bipartite graphs.
Okay, thank you for the introduction.
Go forward, go back.
Okay, thanks. Yes, that's joint work with Gregory Gutin, Enjung Kim, Asu Solimanfala, and Anders Yeo. Yeah, it's about general factors. General factors are a quite well-studied combinatorial thing. What is a general factor? Given a graph G, and for each vertex of the graph, we are given a list of non-negative integers. And now a general factor is now a subgraph f of G, such that for each vertex, its degree in the general factor belongs to the list of integers assigned to the particular vertex. So in our example here, we have the graph with the lists, And now, in this case, indeed, there exists at least one general factor here indicated with red edges. Now, general factors were introduced by Lovász in the late 60s, and general factors generalize in a natural way several other factors. For example, perfect matchings, also known as one factors, are of course general factors where each degree list contains singletons and contain just one integer, namely the integer 1. But there are also other more general concepts of factors like R factors, AP factors, where you have intervals, and so forth. But all these factors listed here, for all these, it's possible in polynomial time to determine whether the graph has such a factor. But it's different now for general factors because it's NP-complete to decide whether a given graph with a given list assignment has a general factor. Yeah, it's polynomial solvable for if the degree lists satisfy certain conditions. For example, if all degree lists are intervals, then you can solve the problem using flow theory. Actually, you can go more general than just intervals. You can allow to have intervals with holes, where the holes are just size 1. So just one integer is missing in a row. This is, if you just restrict the classes of integer lists, that is in a certain way the best you can do. As Cornagels showed in '88 that there is a dichotomy. So whenever you allow degree lists where there are gaps of size 2 or bigger, then the problem is NP-hard, and otherwise it's solvable in polynomial time. Okay, now we look at general factors in bipartite graphs. And actually, this study was motivated from a problem that appears in the context of constraint processing. Namely, there is something called the extended global cardinality constraint, which is used in several commercial and academic constraint solving packages, used for modeling problems. Namely, such a EGCC constraint has a set of variables and a set of values. And now each variable has a set of allowed or of possible values. Here indicated in this graph, like x1 can get the value d1 or the value d3. And now here these lists say how often a particular value is taken by variables. So for example, here this means that the value d3 should be taken 0 or 1 time from these variables, but not 2 times. So in this particular setting, this is now a special case of the general factor problem, where we have on the left-hand side just singletons with the integer 1, and here on the right-hand side arbitrary lists. And the general factor problem is already NP-hard for this particular type of instances. And even the right-hand side, if you restrict the right-hand side to lists of this type, then it's already NP-hard. It's easy to see that you can express three-dimensional matching with such general factor problems. Okay, just a word on global constraints. There are a lot of global constraints used by these constraint solvers, and each constraint has some special combinatorial algorithm built in. And now people model problems by putting several of these global constraints together. So in a certain way, if you develop an efficient algorithm for one of these global constraints, then your algorithm is used or can be used in a very general context for a lot of different problems. So that's something quite worth to look at also from the parameterized complexity perspective. And here that's from the global constraint catalog from the index, just the first page. As you see, there are a lot of different constraints, all different constraints, and so forth. So I think that's quite an interesting area to consider for fixed parameter algorithms. Okay, now how to parameterize this constraint. So in the previous work, we parameterized it by the tree width. And it turned out that it's W1 hard. It's in XP. You can solve it in polynomial time for fixed bounds on the tree width, but not fixed parameter tractable. And now here we parameterize by the number of values. So in other words, the parameter is the size of the right-hand side of our bipartite graph. And yeah, by the way, this was kind of funny when we submitted this paper to a constraints journal with the tree width as the parameter. The referee said, now is this very reasonable to assume that this graph is tree-like? But then we answered, yeah, but consider the number of values bounded. Then the tree width is also bounded. And so that did the trick. So we have here a less general parameter, but we can show fixed parameter tractability. And in particular, we show it for a slightly more general setting than the extended global cardinality constraint. So the degree lists at the left-hand side should be singletons, but the singletons are not necessary singletons containing the integer 1 only. The singletons can contain arbitrary integers, and we showed that this is, in a certain sense, the best you can do. When you allow lists of size 2 on the left-hand side, then the problem becomes already W1 hard. And so our paper contains mainly two results, the FBT result and the W1 hardness result. And the rest of the talk is devoted to just giving the ideas how these two results are obtained. Okay. Yeah, and of course the FBT results applies to the constraint. Okay, now for the FBT result, the outline of the algorithm is as follows. So first we introduce an edge-weighted version of the problem. This appeared to be very essential and made things much easier than without the unweighted version. Then we have reduction rules that are kind of modular decomposition-related rules. And with these rules, we get from the unweighted to the weighted version of the problem. And then the key lemma, and that was actually really the key that allowed us to get the FBT result, was to show that if the weighted instance has a solution, then it has an acyclic solution, where acyclicity I will define as what we mean here by acyclic. But that was really the key, and now we can find an acyclic solution by dynamic programming. Okay, now the first step for the algorithm are the edge weights. So we are just giving an edge and non-negative integer weight, and the intuition behind the weight is just that an edge of weight W represents W many parallel edges. And so therefore we can consider an unweighted graph as a weighted graph with unit weights. And a general factor now of such an edge-weighted graph is another weighting f, which assigns to each edge an integer Fe, and this integer must be at least as big as the weight of the edge. So like here, if the weight is 3, then the factor can take here at most 3 for this edge. And of course, it's natural how to define now the degree of a vertex. It's the sum of the weights of f for all incident edges. And it's now f is a general factor if this degree belongs to the assigned list for each vertex. Okay, now to the modules. A subset M of the left-hand side of our graph is a C module if all the vertices have assigned the singleton containing C, and all these vertices in M have exactly the same neighbors. So here on the right-hand side we have such an example of a C module, but think of this as embedded in a bigger graph. But here these vertices, all neighbors are shown, but these two vertices could have other neighbors, of course, on the left-hand side. And yeah, and the edges here should also all have unit weight. And now it's a very natural thing to do, to just collapse the module to a single vertex and to calculate the weights as you would expect. So here we sum up the singletons here and represent now this new vertex with this accumulated singleton. Okay, now actually you might think we are almost there. We just do this contraction. Now the right-hand side, the parameter is at most k. So that means when we contract maximal C modules, we end up with at most k times 2 to the k vertices on the left. So we have a kernel. We have the number of vertices now bounded by k. So we are done. No, we are not done, because the degree lists on the right-hand side can be arbitrarily large. And so actually the hardness of the problem that we still need to solve is encoded in this very long degree lists on the right-hand side. Okay, now to the acyclic general factors. Now to define it, let's consider the concept of a skeleton of a general factor f of an edge-weighted graph. We take a spanning subgraph of G consisting of all edges that are neither empty nor full in the general factor. So all edges that have a value that is bigger than 0 and smaller than the capacity given by the edge weighting W. And now we call a general factor to be acyclic if its skeleton is acyclic. And the key lemma is now that if the edge-weighted graph has a general factor, then it has an acyclic general factor. And the proof is actually not very difficult. Assume we have a cycle in the skeleton, here displayed. Then we take an alternating cycle construction, similar as you know this from matching theory. We shuffle the value 1 from the weight of in the factor of the first edge. Actually, we shuffle something from down up to the first edge. Now that this still remains a value, a correct factor, we also need to repair it. So we shuffle and shuffle. And when we have closed the cycle, then all vertices on the left and on the right have exactly the same degree in the factor as before we started this reshuffling. So in other words, we turned one general factor into another. But the trick is now that we consider general factors that are maximal in the lexicographic ordering, where we order all values when we visit the edges, when we cut the graph like here. So this edge would be come before that edge. And because it's also the first edge that we change, so we actually increase the lexicographic ordering of this factor. And therefore, when we assume from the beginning that the general factor is maximum in the ordering, we can't find such a cycle. Actually, this reminds me a little bit on Toby Walsh's talk, because he had also this lexicographic orderings for symmetry breaking. So maybe this is conceptually somehow related to the symmetry breaking he was talking about. But here, actually, this is only for us. That is not an algorithmic step. It's just an existential theorem. Okay. Yeah. Now we can do dynamic programming when we assume that our result is acyclic. So when we have this acyclic skeleton, then we can start at leaves of the tree or forest and process the leaves, because for each leaf we know what to do with it. Let's consider this example. So we have here the leaf and its unique parent, and when we want to find the general factor, we know that all to achieve these degrees, it must be achieved via this edge. So therefore we can just consider the cases. Either we get degree 2. This would mean that here actually this becomes 1 minus 2 is smaller than 0, so this doesn't work, but we can achieve degree 4 here. That means, but when we subtract 2 from 4, we get 2, and yeah, and this gives us here this number 2. And the second possibility is if this vertex gets degree 4, then here this doesn't work, but here with 4 it works, and we get the new value 0. So 2 and 0 are the new integers in the list of this vertex, and we can delete the leaf. And now we repeat this. Of course, we also need to take into account the capacity of this edge. If it's too small, maybe some of these integers can't be used. But it's easy to see that now in polynomial time, or actually in linear time, we can, when we are given this acyclic skeleton, we can check in linear time whether or not there exists a general factor that with this particular skeleton. Okay, now we can state the full algorithm. So first we are given this unweighted graph. We just add unit weights to the edges. We get the weighted instance. Then we contract maximal C modules. We get our vertex kernel, but still, as I said before, with this possibly long lists of integers. Now we guess full edges. That's quite the important part here, because when we do our reshuffling along the cycle, we increase the weight of every second edge. If this edge would already be full, we can't increase it. Therefore, we must avoid this case. But as we have already a bounded number of edges, we can afford to non-deterministically guess these full edges. When we know that an edge is full, we know how to process it, how to update its endpoints, and so we can get a new instance where these full edges are deleted, and of course the integer lists are updated. And second non-deterministic step is we guess a spanning forest, and now we solve this acyclic instance with dynamic programming. So everything here except for step 3 and 4 is very easy. 3 and 4, of course, are costly. And when you compute the running time, you arrive at some rather ugly thing like this. So when this is the general case where the singletons on the left can be arbitrary, when the singletons contain just the integer 1, as for the extended global cardinality constraint, then actually the step 3, you don't need step 3, and then you can get rid of this red part in the complexity estimation, and so it gets slightly faster. But nevertheless, this is a classification result and not really a result for a practical algorithm. Okay, now briefly to the W1 hardness. So we assumed in our algorithm that on the left-hand side, all these lists are singletons. Is this necessary? Yes, it is. Sorry, it should be W1 hard. The general factor problem is W1 hard for bipartite graphs when the degree lists on the left-hand side have maximum size 2. And so in particular, our reduction shows that all vertices on the left have these 2 types of degree lists. So they are still quite restricted. We show this by a reduction from partitioned clique, also known as multicolored clique. So just a rough picture how this works. So this is an example for k equals 4. The multicolored clique problem the instance is given by a set of k independent sets of same size n. And so the edges of the graph run only between these sets. And we are looking for a k-clique there. And the k-clique, of course, looks something like this. So in order to find the k-clique, we have to do 2 things. We have to do a selection for each partite set. We have to select exactly 1 vertex. And we have to do an incidence check to check that the vertex selected in one set is adjacent to the vertex selected in each other set. And now the idea is that we encode this problem with numerical values. So it's kind of also clear from the algorithm that we need to use these long integer lists to actually encode our problem. And we do it this way. So we represent each partite set with something we call a selection gadget. So the selection gadget will just select a certain number of edges. And this number represents the number of the vertex in the set. So if it's number 3 here, that means we take the vertex number 3 in this set. And the incidence check is now made by in the following way. We associate with this vertex a degree list that consists of all of the sums of pairs B and C where B and C are adjacent in the instance graph of the clique problem. So, but we multiply B by n so that the sum represents uniquely the pair B and C. And so for each of these vertices, we choose one side as the kind of the big side where we multiply the numbers by n, and the small side where we don't. And yeah, So this incidence check, actually these lists now encode our given graph. The graph without the degree lists are generic for every k and n. Okay, here is just a rough sketch of the selection gadget. Yeah, it's yeah. I think I don't go into details, but as you can see, it's not very complicated. Here, the left-hand side just multiplies when we select one integer here. Then this number, this degree, is kind of multiplied to these output vertices, and by putting two such selection gadgets together, where one side has these multiplied numbers, then we can encode the problem. So I just quickly, as the time is running out, quickly jump to a summary slide. So I've shown this FBT result and W1 hardness result for general factors. It applies to the extended global cardinality constraint. The FBT result is a classification result, not a practical algorithm. And very quickly, some research questions. Of course, can we improve the algorithm, get something really practical? Other parameters for the same problem, for example, parameter could be the size of the class U, or similar to Cohn-Mageau's theorem, we could also look at the problem where the integer lists belong to certain classes of integer lists, like gaps of a certain size are forbidden and similar. And of course, the constraint catalog has over 300 constraints, so there is still a lot of more area we could apply our algorithmic ideas to. Okay, that's all. Thank you for your attention.
Thank you. So maybe a very quick question. We are a bit late, if any. Yes?
Just a bit, you said it was W1 high for Phoenix. Is there anything about Patrick? Is it high for Patrick as well?
I don't know. The reduction there is also from multicolored clique. And so I suppose the reduction keeps, how is it? Actually, I think the path width is also bounded. So it should be also hard for path width.
Okay, let's thank the speaker again. So now we'll have a second talk on a new lower bound on maximum number of satisfied clauses in MaxSat, which is given by Mark Jones.
This one here.
Okay.
You know how to use this. Okay. Thank you. I'll just get straight into it. So the problem we're considering is MaxSat. So you have a conjunctive normal form formula with m clauses over n variables, and you want to know how many of those clauses you can satisfy with an assignment. So in the standard parameterization, we'd ask, can we satisfy at least k clauses? So SADF here means the maximum number of clauses you can satisfy. This is easily shown to be fixed parameter tractable because there's a probabilistic bound that says that you can always satisfy at least half the clauses in a formula. So for that reason, if k is less than m over 2, then the answer is obviously yes. And if it's not, then you have a bound on m. And so it's FPT. But on the other hand, this isn't a particularly useful parameterization because it doesn't really give you a useful algorithm in the interesting cases. The interesting cases are going to be ones where k is bigger than m over 2, so k is going to still be quite large compared to m. So the fact that you have a parameter which is exponential in k is, the fact that you have an algorithm which runs in time exponential in k is not that useful. So a better question to ask is, can we satisfy at least m over 2 plus k clauses? So this is what we call a parameterization above a tight lower bound or above a guarantee. And Mahajan and Raman in 1999 showed that this question is fixed parameter tractable. And I'm going to give a proof of it, but the proof I'm going to give is not the same as theirs. So the only tight case for the m over 2 bound, the only case when you can only get exactly m over 2 clauses is when you have pairs of clauses where one clause says x is true and the other clause just says x is false. And then you know that for any possible assignment is always going to satisfy only one of those assignments and no more, and only one of those two clauses. Sorry. So we can remove such pairs of clauses quite easily. We can reduce the formula down because for any pair of conflicting clauses, just remove them both and assume that one of them will be satisfied, and then carry on. If you've reduced a formula by this form, if you have a formula where there are no conflicts between pairs of clauses, we call that a unit conflict-free or two-satisfiable formula. And there's a bound which says that for a unit conflict-free formula, you can always satisfy at least phi m clauses. Phi here is the inverse of the golden ratio. It's the positive root of the equation phi squared plus phi equals 1, and it's about 0.61. So using this bound, we can show that this question is SAT-F at least m over 2 plus k. We can show that this is fixed parameter tractable because we can quickly reduce the formula to one which is unit conflict-free, and then we use this bound, and this bound tells us that if m over 2 plus k is less than phi m, then the answer is yes, and otherwise, again, we have a bound on m, the number of clauses, and we get fixed parameter tractability. So what we did so far is standard parameterization is, can we satisfy at least k? This is FPT because we have this m over 2 bound. Then we take this bound and say, can we get at least k over that? And this is FPT because we can reduce it to a unit conflict-free formula, and we have a bound for a unit conflict-free formula. So next question we can ask is, can we get k over this bound? For a unit conflict-free formula, can we satisfy at least phi m plus k clauses? And this is a problem that we consider in our paper. So Mahajan and Raman conjectured that it was fixed parameter tractable in 1999, and this has been an open problem since then. So what can we do? The first thing we might want to try is just repeating the same sort of trick as we did before. So we previously took a formula and reduced it to one which was unit conflict-free or two-satisfiable. So we might want to try taking our two-satisfiable formula and reducing it to one which is three-satisfiable. So reducing it to one where for any three clauses, there's an assignment which satisfies all of them. And there is a bound that says for such a formula, you can always satisfy at least 2/3 times the number of clauses. So if we could reduce to this form, we'd be done using the same tricks we had before. The problem is that doing this reduction isn't as straightforward as it is in the two-satisfiable case. We can find a set of three clauses which contradict each other, but we can't assume that two of them are going to be satisfied. Say, the optimal assignment might satisfy one of the clauses, it might satisfy two of the clauses, we don't know. So this approach is unlikely to work. So what we do instead is we do a reduction to another kind of formula. So it's still a unit conflict-free formula, and in addition, it has what we say it has a complete matching from the variables to the clauses, and I'll explain what I mean by this in just a second. And so we do that reduction to that form, and then the second part of the trick is to prove another bound on sat f for that formula. We show that it's at least phi m plus gamma n. Gamma here is this number here, which is it's about 0.07. Okay, so I said we're going to reduce the formula to one which has a complete matching. By complete matching, I mean a complete matching from the variables to the clauses. What I mean by that is take your formula and turn it into a bipartite graph with your variables on the left-hand side and your clauses on the right-hand side, and just draw, excuse me, draw a line between a variable and a clause if and only if that variable or its negation appears in the clause. So, for example, we have this clause here, not x2 or x3 or not x4, so we draw a line to x2 and x3 and x4. So that's pretty straightforward. We say the formula has a complete matching from the variables to the clauses if and only if this bipartite graph has a complete matching from the variables on the left-hand, from the vertices on the left-hand side to the variables on the right-hand side. So this formula here, for example, doesn't have a complete matching, and you can tell that because we've got this set of 5 variables here, and its neighborhood is only, a set of 4 variables here, and its neighborhood is only 3 clauses. So now we do the reduction. Suppose that we don't have a formula with a complete matching. How do we get down to one which does? So just find a minimal set of variables such that it has no complete matching to its neighborhood. So here I've selected these 4 variables here. Their neighborhood is only of size 3, so there's no complete matching from here to here. And it's not very difficult to show that if we pick x to be minimal, then there isn't matching from here to here, but there is a complete matching from here to here. So there is a complete matching which covers all the variables. There is a matching which covers all the clauses containing variables from this set x. And given this matching, we can satisfy all of the clauses here without affecting the rest of the system, because for each clause we just take the variable it's matched with and just set that variable to be whatever it needs to be to satisfy that clause. So I've got a matching here with the matched variables in red. So for the first clause, the first clause contains x2, and x2 is its match variable, so we just say x2 is true. The second one we say x1 is true, and for the fourth one it's matched with x4, but x4 occurs negatively in that clause, so we just say that x4 is false. And so given this, we can, if there isn't a complete matching from the variables to the clauses, we can always find a set of variables and the clauses containing those variables such that we can satisfy all those clauses. So we always just remove a bunch of clauses, assume that they're satisfied, and carry on. And we keep doing this until we have a complete matching. Okay, now the second bit is to show this bound. So given a formula with a complete matching, show that you can satisfy at least phi m plus gamma n clauses. M is the number of clauses and n is the number of variables. I think this bound here is the main part of our paper. It's the clever part of the paper. It's where all the work is done. But the proof is kind of horrendous to try and explain in a presentation format. So I think I would probably skip over almost all of it. It's just, there's a lot of case analysis and some complicated number crunching. But I will just talk about this bit because it relates to the reduction rule we just had. So the first thing we do in showing this bound is we shrink some of the clauses down, and maybe negate some of the literals, so that we get the formula in the following form. So it has two kinds of clauses. For every variable in the formula, there is a unit clause containing a positive instance of that variable. And any other clause is of the form not x, not y for some variables x and y. So this part 1 here, there is a unit clause for every variable x. This is why we need a complete matching from the variables to the clauses, because we want to be able to say that for every variable, there is some clause containing that variable that we can shrink down, and obviously we only want ones we need. We don't want two variables to share such a clause, so each variable needs to be assigned with a unique clause containing it. So that's why we use a complete matching. So how am I doing for time, by the way? Okay. Okay, well then I might go very quickly over the steps we actually do to get this bound. So we define a couple of measures. We define WV of x, the variable x, is the weight of all clauses containing the positive literal x. And WV of x bar is the weight of all clauses containing the negative literal x bar. By weight, I just mean the number of times such a clause appears. So WV of x is all clauses containing the positive literal x, but because of the form we've now got the formula in, this is just the weight of the unit clause containing x. And we also define this measure epsilon x, which is just a way of measuring, of balancing the positive literals against the negative literals. Yeah. So the first thing we do is, if the weight of the positive literal x is bigger than the weight of the negative literals x bar, then we set x to be true. And this is kind of obviously the right thing to do, because WV of x is just the weight of the unit clause. So if you were to set x to be false, you'd definitely lose that unit clause, and you'd be losing more than you could possibly gain from the clauses containing x bar. Once we've done that, we can also show that if this property holds, we set x to be true. 1 minus phi times epsilon of x is bigger than gamma. This is less intuitively obvious. I won't go into why it works. And then for the remaining two cases, we have to construct a graph from the formula. So we let the vertices in this graph correspond to the variables or to the unit clauses, and then draw a line between two variables if and only if the clause containing the negation of those two variables appears. So this formula here has one each of the variables x1 up to x7, and it's got a clause x1 bar or x2 bar. So we draw this line between x1 and x2. If we have any isolated triangles in this graph, then we can just deal with them separately, because it's just a sub-formula with only three variables, so that's easy. If not, then we can show that there is an edge, xy, with the following property. For any other variable z or any other vertex z, the neighborhood of z is not equal to x and y. So we can have things which are adjacent to x but not y, or adjacent to y but not x, and we can have things which are adjacent to x and y but are also adjacent to other things. You don't have a vertex which is only adjacent to x and y and nothing else. The point of this is that it allows us to assign a value to x and a value to y, and this will, and every other variable, once we simplify the system, will still appear in some clauses in the system. So it means that when we set x and y, the number of variables we lose is only 2. We only remove x and y from the system. Yeah, so we measure epsilon x against epsilon of y and assign true to whichever is bigger. So yeah, I didn't expect all of those steps to be obvious, but what we can show is for each of those steps, if you look at the number of clauses that you satisfied and you look at the number of clauses that were removed altogether and the number of variables that were completely removed from the system, the number of clauses you satisfied is at least phi times the number of clauses you removed plus gamma times the number of variables you removed. And so if you put that all together, once you've finished with your system, you have that you've satisfied at least phi m plus gamma n clauses, and this is the bound that we wanted. So that's that bound. So just to go over what we did, the question was, for a unit conflict-free formula, can we satisfy at least phi m plus k clauses? We reduce the formula to one which has a complete matching. And then, given it has complete matching, we use this bound. So if k is less than gamma of n, we know that the answer is yes. And otherwise, we have that n is bounded by k over gamma. And this means that we can exhaustively try every possible assignment in time 2 to the k over gamma. And so we get fixed parameter tractability. And we get a kernel with a linear number of variables. I also just need to mention briefly, because the title of the talk is an improved lower bound on a unit conflict-free max set, that this bound that we get also gives us a bound for the original unit conflict-free max set. It's not just a bound on a unit conflict-free formula with a complete matching. But yeah. So yeah, the problem is fixed parameter tractable. So this is just how it fits into what went before it. Standard parameterization is FPT because of this m over 2 bound. M over 2 plus k is FPT because of this phi m bound. And phi m plus k is FPT because of this phi m plus gamma n bound. So the next, okay, fine. The next question we might want to ask is, for a unit conflict-free formula with a matching, can you satisfy at least phi m plus gamma n plus k? This would be fitting into the pattern of parameterizing above a new bound. But we don't have any particular ideas on how we'd go about solving this one. The other approach to try the other kind of obvious next open problem to consider is, so this problem was on 2 satisfiable formulas. Any 2 clauses can be satisfied. What about 3 satisfiable formulas? It's known that for such a formula, you can always satisfy at least 2/3 of the clauses. So can you satisfy 2/3 plus k? And this is what we're working on now. OK, that's the end of my talk. Thank you.
Thank you. So we are a bit late, but one talk is cancelled in the second session. So maybe one question before our break. Yeah, Yannick?
Did you somehow look into this notion of author keys, which you said other people sometimes at least use?
I don't think so. Sorry, which notion? Articles?
Author key. That's especially used by Oliver Kuhlmann and his colleagues, I would say. And I'm pretty sure that your matching stuff is a special case of an author key.
Okay.
And so they have tried kind of theory also for MaxSet for these author keys, which might fit into this picture.
Okay, I'm not familiar with that, but it doesn't surprise me at all that this matching reduction has been done before. So, but that's interesting. I'll ask you about that afterwards.
Stefan?
Yes, actually I wanted to comment. In fact, this is known as matching order key reduction. What you do to get the formula with the complete matching, as you call it.
Okay. Okay, thank you.
Okay. So, any more comments? So let's thank the speaker.